Hello, welcome to the next video lecture on strength of materials.
Expression for deformation in the bar due to its own weight. Let us consider a vertical bar as shown, which is having a cross-section area A and length L fixed at one end. In the first case, it is fixed at the bottom end. In the second case, it is fixed at the top end. Both the cases are same. Let us assume that Young's modulus of this material is E and density of the material is rho. Density is required because we are trying to account the self weight. So this is density. Now, in order to derive the expression, we have to consider a small element here, small elemental length here. In this case also I can do it. Let us consider the distance of this element from the free surface here as x. The length of this small element that we have considered, that we will take it as dx. Dx is the length of the element that we have considered. And in the other case also I can do that. X from this end and this is dx. We will try to find out what is the load that is acting at the element. At the element considered, we just observe at this element in the first case, this is case A, this is case B, let us say. Both are same actually. If I take the element here, what is the load that acts at that element? It is the weight of this portion of the bar that acts on it. In case B, this is the portion which applies the load on the element. So if I write the load acting is equal to, how do I write the weight of that portion? It is volume of the portion. I'll call this as ABC. Volume of portion BC into density of the material into gravity. This is the total load acting on the element. Volume of that portion BC is what? Cross section area is A into the length. Length of that portion is X. A into X is the volume of the portion BC into the density of the material is rho. It is a material property into gravity G. So this is the load acting on the element. Now I can write what is the deformation in the element. I'll call it as PLX. For the element, PL by AE can be applied. So P is the load. Load is A into X into rho into G. This is the load that is acting on the element. This is P into L. L for the element is dx divided by A into E. A is the cross section area, E is the Young's modulus. I can cancel A here and write this as rho dx dx divided by E. This is the deformation in the element. Now I want the deformation for the entire bar. So total deformation in the bar dl, which should be integration of dlx. It is integration from 0 to L of rho gx dx by E. If I take all the constants outside, rho g is constant, E is also constant. Integration of x dx is x square by 2 between the limits 0 to L. Now if I substitute the limits, I'll get rho g L square by 2E. So dl is equal to rho g L square by 2E. This is the deformation in the bar due to its own weight. We will consider one case. We will take vertical bar like this. It is having a length L, cross section A, Young's modulus E, density rho, let us say. Now we will not take the distributed load, but instead assuming total weight of the bar. W is equal to volume into density into gravity. Volume of the bar is L into A into density is rho into gravity. This is the total weight. Now if I assume that this weight is acting at the end, LA rho G, if it is acting at the end, the normal equation that we use for DL is equal to PL by AE. In place of P, if I substitute this L A rho G into L divided by A, A will be cancelled, becomes L square rho G by E. Now I just try to compare this with the previous expression. Compare this with the expression here. So what is the comparison? Comparison says that deformation in a bar due to its own weight is half of the deformation in the same bar when the total weight is assumed to act at the free end. So I will write a sentence for this comparison. Extension produced due to self-weight of a bar of uniform cross-section fixed at one end and suspended vertically is equal to half the extension produced by the load equal to self-weight applied at the free end. This is the sentence that can conclude.